So in this video, we're talking about the tangent line, so 11.3. So what exactly is this tangent line? Basically, a tangent line is talking about slope, and it's finding the slope of a line, and that indicates the rate at which a line is going to rise or fall. So besides a line, the rate of change changes from our point to point. Okay, so you can see this little image, and this comes from your textbook. And so you can see different points, so point 1, point 2, point 3, and point 4. And we can kind of see this red tangent line and how it is increasing, right? How either the slope is increasing or decreasing, getting to 0, or even becoming negative as the point kind of goes around the parabola. So again, what it basically is saying is that this tangent line to the graph, which is in red, is a line that best approximates the slope of the graph at that point. Okay. And so again, if this graph had numbers, we can kind of use our best judgment to figure out what that slope is. So again, here's some more examples of what tangent line looks like. So we can see again, point P is our line, is our point of tangency, where it's just going to touch your graph at one point. So we can see that this is on our first graph. On the left, we can see a positive slope, right? So we can say positive slope. Here we can say it's a negative slope. Again, there's no number, so we can't approximate it. And then this one is no slope. So our m is equal to 0. That one we for sure can say. And if we recall, slope is the change in y over the change in x, right? Which is aka y2 minus y1 over x2 minus x1. So hopefully something that we are thinking about is this. How do you find the slope of a line from just one point? And that's a really good question. How do we do that? So how do we find this tangent line's slope, especially if we're just kind of approximating it? How can we be a little bit more accurate? Well, what we can do is we can actually find the secant line. So the secant line is finding the slope through the point of tangency and a second point on the graph. So here's a picture of the difference between a tangent and a secant line. So the tangent again is the one that's kind of in dark purple or dark blue, and it's just touching this point right here, which is the point of tangency. Now notice the red line. So notice the red line is touching on this graph at 2 points. So the point of tangency and up here, a second point. Now, does it look like the slope of the tangent and the slope of the secant line are equal to each other? So I'm going to say slope of the secant. Does it look right now, just by looking, does it look like these are equal to each other? And hopefully, of course, you're going to say no. The tangent line and the secant line are not the same slope. But what happens if you kind of moved this closer and closer to this point? So if we made this point here instead, or here, or got super, super close to the point of tangent, wouldn't then the secant line start to look like the tangent line? And the answer is yes. Yes, they would. So I have a little animation that kind of shows this. Okay, so we can see our secant line, we can see our tangent line, and again, see that second point as it's getting closer and closer to 0, right? So I'll pause it really fast. So we can see again the difference between the 2 points. They're far away. I'll unpause it. And now we have a secant line, and we can see that the point is getting closer and closer. So this line is getting closer to that tangent line, right? Again, let's do it one more time. Secant line moving closer and closer until we get to that very end, right? Close where it's approximately 0, but we're not going to see that the change in x is 0. So here's a better description of what's happening. And this comes from your book, okay? So again, we see and I'll pause this. We don't need to keep watching my little graphics. right? So here's all of the points of tangency highlighted in yellow on all three graphs, okay? And then the second point, our secant point, right? We're going to get closer and closer to my yellow point. So notice that the blue dot's moving closer and closer to this to the yellow dot, and once it gets practically on top of it, it turns into the tangent line. Okay, and the biggest thing to remember is that your x value, right, is changing by adding an arbitrary number, which we're going to call the letter h. So x2, x plus h, again, that's the change in x. And if we plug in an h, if we add it to the x, then I'm also plugging it into my y value. And so we're going to notice that this is really the change in y. So we have a formula. We know what the slope is, right? Slope is change in y over change in x. The only difference is we're going to use a different way to write the change in y and the change in x. We're going to use a limit. And this is the definition. So we're saying our slope is the limit as h approaches 0 of our slope of our secant. So we have an equation where we're saying f of x plus h minus f of x. Again, this is your change in y. And then just your h is on the bottom. And this is your change in x. So again, all it is slope. So what happens with limits? We plug in that 0 in for h. So let's see what happens when I do that. All right, so x plus 0, that's just going to give you f of x. And if you get f of x minus f of x, you're going to get a 0 on the top and a 0 on the bottom. If we recall from 11.2, evaluating limits, this is what's known as the indeterminate form. We cannot tell what this limit is. So there has to be another way that I can solve for it. So basically what we're going to work on in this video is we're going to try to figure out how do I get rid of that h out of my denominator. Because if I get rid of that h in my denominator, chances are I'll be able to get rid of it in my numerator and actually be able to plug in the 0. So let's see what we can do. So here's our first example. We're going to find the slope of f of x is equal to x squared, which is a parabola, at the point -2, 4. So again, I've copied down our slope formula right here. And we've already plugged in the 0 in for h. We've just did it right here. And I'm going to get the indeterminate form. So what else could I do? Well, I have another letter in there, and that letter happens to be x. I have an x here, and I have an x here. And notice I gave you a point, and I have an x there. So what I'm going to do is I'm going to plug in the -2 in for x. So f of -2 plus h minus f of -2 all over h. Again, if I plug a 0 in, this is going to cancel, leaving me with indeterminate form. The 0 is not out of my denominator yet. So what else can I do? So off to the side, I'm going to do a little bit of work. So anything in a green box does not really follow the progression that I'm writing in black over there. But what I'm going to do is I'm going to evaluate this function for -2 plus h. So that means everywhere I see an x, I'm going to plug in -2 plus h. So this gives me -2 plus h times -2 plus h. So negative and a negative turn positive. This will leave me with -4h and then plus h squared. Okay. I'm also going to evaluate the function at -2. Now the great thing about -2, it's already here. It's already 4. But just to make sure, if I plug in -2 and I square it, I do in fact get -4. So color coordinating it, this guy right here is going to be replaced right here. And this guy right here is going to replace that right there. So what does that look like? The limit as h approaches 0 of, and I'm going to use parentheses for the most part, very important, and then all over h. Well, I still have a denominator of h, so I'm gonna distribute the subtraction sign. Now, most people can do this step of distributing the subtraction sign in their head, or we can just erase the parentheses. But I like to show this step. And then notice that I'm going to be able to get rid of this 4 and this -4. So this becomes the limit as h approaches 0 of -4h plus h squared all over h. Okay, I still haven't gotten rid of the h yet, but notice I have h's in the numerator on both things. So I ran out of room down there, so I'm going to bring it up over here. So what I'm going to do is I'm going to divide the h into everything. So it becomes -4 plus h. Now, if you don't know how I got that, what I'm really doing is I'm factoring out the h from everything, right? And then the h and the h cancels away. So now I do not have an h in my denominator, so now I can actually plug this guy in. So -4 plus 0, so that's going to give me -4. Okay. So why don't you try to head and pause the video and try to do this example on your own and see if you get the same number that I'm going to get. Okay, so if we try plugging in a 0 in for h, again, we're going to get the indeterminate form. So I'm not even going to worry about this. So what I'm going to do is I'm going to plug in the 2 in for x. And just so happens my first two examples, I picked 2 and -2. I did not do that on purpose. Okay, so now off to the side, again, in green is not following things linearly. So I'm going to figure out what is f of 2 plus h. So this is really 2 plus h squared, or sorry, cubed. Last one was squared. So this will be 2 plus h times 2 plus h times 2 plus h. So we're going to get 4 plus 4h plus h squared. And then I'll multiply it by 2 plus h. So I'm going to get 8 plus 4h plus 8h plus 4h squared plus 2h squared plus h cubed. Collect my like terms. I'll start with the highest degree, power 3, and then I get 6h squared plus 12h plus 8. And then f of 2 will just be 2 cubed, which gives us 8, which is what we already had. So again, I'm color coordinating it. This guy is going to go right here. And this guy is going to go right in there. So the limit as h approaches 0, parentheses h cubed plus 6h squared plus 12h plus 8 minus parentheses 8 all over h. So again, if I distribute just like the last problem, I'm not necessarily needing my parentheses, so I'm going to get rid of my parentheses. And I will notice that the 8 and the -8, they cancel away. The limit as h approaches 0, h cubed plus 6h squared plus 12h all over h. h's are going to cancel away. Finally, I'll be left with h squared plus 6h plus 12. And now I can plug it in. So this will become 0 plus 6 times 0 plus 12. So my slope is just 12. So if you got that answer, great. If you didn't, try to see what you did on your work versus what I just did. Now, we're not always going to find the slope at a specific point. Sometimes what we want to do is find a slope formula that will work for any point on our graph. So that's what we're going to do on this next question. So I want you to treat this as two separate things. So what's boxed in brackets, red brackets, we're going to focus on it a little later. So the first thing we want to do is we want to find the formula for the slope of this parabola, x squared plus 1. And notice, and if I didn't give you the brackets, we can still find the slope formula. So basically what we're going to do is we are not going, so don't plug in a value in for x. So we're not going to plug in a value in for x. So what are we going to do instead? Well, what we're going to do off to the side is this, okay? I already have something plugged in into my function. I already have an f of something. I have an f of x plus h. So let's go ahead and plug in x plus h everywhere I see an x. That's already there, so why not use it? So this will give me x plus h times x plus h, then plus 1. So this will give me x squared plus 2xh plus h squared, right? It is a perfect square trinomial. And then I have this plus 1. So this expression right here is what we're going to plug in right there. Now, for the f of x, well, the good news is I already know what f of x is equal to. F of x is equal to this guy right here. So I already have everything that I need to plug in. So the limit as h approaches 0, and then parentheses x squared plus 2xh plus h squared plus 1, then minus x squared plus 1 all over h. So this is why we need parentheses, because now notice on this example, there is a subtraction sign in between a binomial and the polynomial. So I'm going to need to write a second step. I can't just eliminate my parentheses. I have to distribute. So the x squared becomes negative, and so does the 1. But notice, the x squared goes away. Those are going to cancel out, and the positive 1 and the negative 1 will cancel away. So things to keep in mind, anything that's in the second parentheses should always go away. The limit as h approaches 0, 2xh plus h squared all over h. I still need to divide it out. So the limit as h approaches 0, this will just be 2x plus h. Can I plug a h in? Can I plug a 0 in for h? Absolutely. So my slope formula is going to be 2x plus 0, or aka just 2x. So here's my slope formula. So what can I do with my slope formula after I find it? Good question. Now we can focus what was in the brackets. Now we're going to find the slopes at these points. So this is the easy part. Once you find all the hard part, now this is the easy part. So at the point -1, 2, I am going to plug in the -1 in for x. So I get my first slope is -2. At 2, 5, I'll do the same thing, right? Oops, let me write that a little bit better. So m is equal to 2 times 2, so m is equal to 4. So at 2 different points on this parabola, I have 2 different slopes, but they're all found using the same slope formula. All right. So last but not least, let's try one more example. So find the formula for this slope. So find the formula for the function f of x is equal to -2x plus 4. And again, try pausing the video and coming unpaused when you found your slope. Okay, so hopefully, if you unpause the video, you want to know what your answer is. So if you found your slope formula, the formula should be m is equal to -2, and that's it. This is your answer. Now, there's 2 ways that we can approach this. The first one is the easy way. If you recall, one of the first things I wrote down on the very first slide, I said besides lines, the rate changes from point to point. So beside a line, the rate's going to change. But on this example, it's a line, has to have a negative slope, so something that probably looks like this. So it doesn't matter, any point on this line, they're all going to have the same slope. It's going to be of -2. So you actually didn't have to do any work. But let's go ahead and let's prove that it actually is negative 2 by finding the limit. All right, so the first thing I'm going to do is I'm going to replace in parentheses x plus h and then plus 4 in my first function. And then my second function, I'm just going to write down the negative 2x plus 4 all over h. So this is another way that we can do it instead of writing it off separately. So limit h approaches 0. This will be negative 2x minus 2h, and then just plus 4. So don't distribute that negative 4 to, or sorry, negative 2 to the 4. Negative negative will turn positive, so 2x, and this will give you negative 4 all over h. Notice, positive 2x, negative 2x. Those are going to cancel. Positive 4, negative 4. Those will also cancel. The limit as h approaches 0 of negative 2h over h, those guys are going to cancel, leaving you with just the limit as h approaches 0 of negative 2. Well, the good news is there's no h value to plug in. It's a basic limit function, and that is why this answer is negative 2. Okay. All in all, basically what you're finding, and this is where I'll leave it, you don't have to copy this next slide down, but something to kind of keep in mind. When you find the slope formula, basically what you're doing is you're finding what's called a derivative of a function. And this is the start of a little bit of calculus. So I'm planting the seed for later. If you ever take a calculus class, that's what we're finding. We're basically finding the derivative when we find our slope formula. Okay, so all of these problems, you just found the derivative of this function. M is equal to 2x. This is really the derivative of this function. And that's all.